For pretty much our entire lives, we've lived in this world of digital magic, right? We just expect that every new phone, every new computer is going to be smaller, faster, and way more powerful than the last one. But what if that incredible exponential ride is about to hit a brick wall, a wall that's made of physics itself? Today, we're going to dive into why the very foundation of our digital world is starting to show some serious cracks. And hey, that's not just me saying it. That's the CEO of NVIDIA, putting the problem about as simply as you can. For decades, the entire tech industry's playbook had one main strategy: make everything smaller. But we're getting down to a scale that is so ridiculously tiny, the fundamental laws of nature are basically yelling, stop. So, to really get why we're hitting this wall, we need to rewind the clock a bit. We gotta look at the golden rule that got us here in the first place. For half a century, one simple idea, one observation, drove the entire digital revolution. And that idea was Moore's Law. Now, here's the most important thing to remember. Moore's Law was never a law of physics, like gravity or something. It was just an observation, a prediction really, made by Intel co-founder Gordon Moore way back in 1965. But it became this incredible self-fulfilling prophecy for the whole industry. It was the roadmap everyone used to plan the future. And man, was that roadmap successful? Just look at these numbers. We went from a few thousand transistors in the 70s to tens of billions today. All of that power packed onto a tiny sliver of silicon smaller than your fingernail. This insane exponential cramming session is literally what made our modern world possible. But Moore's Law had a secret partner, a kind of magic ingredient called Dennard scaling, and this part is absolutely key. It basically said that as transistors got smaller, they also used less power and created less heat. This meant we could pack them tighter and tighter together without the whole chip just melting. Smaller, faster, and cooler, it was the perfect trifecta. It was the magic that made Moore's Law work. For decades, this dynamic duo worked perfectly. But then, right around 2005, we hit the first major speed bump. The first big crack appeared in this golden age of scaling. This is where that perfect relationship, well, it started to fall apart. To put it bluntly, the magic just stopped. That perfect trifecta of smaller, faster, and cooler, it broke. Dennard scaling, the very thing that kept our chips from overheating as they got denser, it just stopped working. So here's the heart of the problem. The promise was always that smaller meant more efficient. But the new reality after 2005 was totally different. As transistors got even smaller, they started to leak electricity. Think of it like a faucet that you can't quite turn all the way off. All that leaking current meant they weren't getting more power efficient, and all that wasted energy turned into heat. The industry had slammed right into what they call the power wall. And you know what? This isn't some abstract problem for engineers. You've probably noticed it yourself. Ever wonder why the speed of your computer's processor, the clock speed, kind of stalled out? Why we didn't go from 4 gigahertz to 20 gigahertz? This is exactly why. We simply can't cool the chips down. The end of Dennard scaling forced engineers to find performance gains somewhere else, like by adding more cores to a chip. But that power wall, it was really just a symptom. To understand the root cause, we have to go even smaller. We have to leave the world of engineering and enter the seriously weird world of quantum mechanics. I mean, why? Why did these transistors, which had behaved so predictably for decades, suddenly start misbehaving and leaking all over the place? What fundamentally changed when we made them so unbelievably small? The answer has a wild name: quantum tunneling. Okay, so in our normal world, if you throw a baseball at a wall, it bounces off. Simple. But in the quantum world, things get weird. If that baseball is an electron, and that wall is thin enough, there's a very real chance the electron can just, poof, appear on the other side. Honestly, this is the perfect way to picture it. Transistors are basically just tiny on-off switches, and they use little insulating walls to stop the flow of electrons when they're off. But when those walls get down to just a few atoms thick, the electrons stop following the rules. They start acting like little ghosts, just tunneling right through the walls that are supposed to hold them back. And this isn't just a theory. We know the exact physical limits. Once that main insulating wall, the gate oxide, gets thinner than about 0.8 nanometers, that ghostly tunneling becomes a flood. And once the transistor itself gets shorter than about 7 nanometers, the electrons just start skipping the switch altogether, tunneling straight from the start to the finish. All of that leakage is wasted power, and all that wasted power creates heat. And there you have it. You're right back at the power wall. So yeah, we've hit a pretty solid physics wall. But even if we could somehow invent a way to bend the laws of quantum mechanics to our will, there's another, maybe even bigger wall waiting for us: cold, hard cash. So meet Moore's other law, sometimes called Rock's Law. You can think of it as the economic shadow that's been following all this progress. It basically says that as chips get exponentially harder to make, the factories you need to build them get exponentially more expensive.
Just take a second and look at that number: $20 billion. That's what it costs to build one single factory to make the most advanced chips. The cost is so astronomical that only a tiny handful of companies in the entire world can even afford to be in the game anymore. That creates an economic barrier that's just as real as the physical one. So if we're hitting a wall of physics and a wall of economics, does that mean progress just stops? No way, not at all. It just means the game is changing. The industry is having to shift its whole focus from just making things smaller to making them a whole lot smarter. This is the multi-billion-dollar question that the smartest engineers on the planet are trying to answer right now. If the easy path of just shrinking everything is gone, what's the new way forward to make our technology more powerful? And the answers are pretty cool. Instead of just building wider, like a single-story house, engineers are building up, stacking layers of circuits on top of each other in 3D, like skyscrapers. They're also hunting for entirely new materials to replace silicon, things that might behave better at these tiny scales. And maybe, the biggest change of all, they're designing specialized chips, smarter chips, built to do one thing, like running AI, and do it incredibly well. So what's the big takeaway here? It means that nice, predictable, 2-year rhythm of Moore's Law, it's ending. The era of just brute force shrinking is over. We're now entering a new age, an era of creative design, new materials, and clever, specialized architectures. The next 50 years of computing probably won't be about making things smaller, but about making them fundamentally smarter.